Today we have third lecture in the series of lectures on Six Sigma. Your teacher is Dr. Subhash Kakkad, PhD from Delhi University FMS, MBA from FMS, BE Mechanical from FMS, Six Sigma Master Black Belt and SAP R3PP Consultant. Today we will devote some time on learning what exactly is Six Sigma. It is in continuation to the yesterday's lecture. Then we will also study quality control tools in detail. First, I would like to further explain the Six Sigma level and the measurement scale of Six Sigma. Let us have some example. Suppose the tolerance limits on a dimension are 5 plus minus 0.012. That is, the range is now 4.998 to 5.012. Data are collected from the process during second shift in the industry, which indicates that the process mean is 5.000 and its standard deviation is found to be 0.004. As we know, standard deviation is given by the symbol sigma. That is why we have written sigma is equal to 0.004. Note that plus minus 3 sigma fits inside the tolerance, because plus minus 3 sigma is nothing but 3 into 0.004 and it is 0.012, which is our tolerance limit given by the customer. In the earlier statement, we have mentioned it 5.00 plus minus 0.012. This clearly shows that this fits into the process standard deviation. Standard deviation is 0.004 plus minus 3 sigma are 0.012. The traditional way to calculate yield in this situation is to use standard normal table to find out the area under the normal curve between plus minus 3 sigma. And if we see it on the table, this gives a yield of 0.9973, and this is a usual figure which is given by plus minus 3 sigma level. Let us discuss some statistics and the statistical background regarding this normal distribution and out of range specifications, out of range percentages. This curve is a normal distribution, which is a bell shaped curve, and this curve is symmetrical on both the sides. And now I have shown plus minus 3 sigma limits on this normal distribution curve. And now I have specified lower specified limit as well as upper specified limit on this graph, and these limits are given by the customer and the process limits are given by plus minus 3 sigma limits. Now, if lower specified limit and upper specified limit covers plus minus 6 sigma, where process covers only plus minus 3 sigma. Now, if we see the process plus minus 3 sigma levels, out of range is only 1350 ppm on both sides, on negative side as well as on the positive side. 1350 is nothing but 0.135 on both sides. As we have already discussed in the previous slide, the yield is 0.9973. If we subtract it from 1, it is 0.27, which is nothing but 0.135 on the both sides. and these are the ranges where defects are there, and within these limits plus minus 3 sigma, all the items which are produced are acceptable as far as the process is concerned. Now, if we see the lower specified limit and the upper specified limit given by the customer, which is plus minus 6 sigma limits, if we go beyond plus minus 6 sigma limits, we have only 0.001 ppm on both sides, and these 0.001 ppm is nothing but we call it defects produced in the process. Now, we have a process which is ranging between plus minus 3 sigma, and the limits given by the customer are spread over plus minus 6 sigma. Our process is operating well within the specified limits of the customer. If we go out of these specified limits, only then we shall be producing defective pieces. And if we see the tables, it is only 0.001 ppm on both sides. ppm is nothing but parts per million. Our process is running well within this range, which is spread over only plus minus 3 sigma. Now, if such is the case, 6 sigma allows for unforeseen problems and longer term issues when calculating failure error or rework rates. Why rework? Because if defectives are produced, somebody will have to rework those items to make them acceptables. Let us go to the previous slide. If the specifications specified by the customer are spread over plus minus 6 sigma and our process is spread over plus minus 3 sigma, then the sigma level of the process is called 6 sigma. Experience indicates that the process mean does not remain constant. Now, manufacturers will tell you that while operating the machines or operating the process, the mean does not remain at a constant location. It keeps on shifting, maybe depending upon the condition of the machines, maybe depending upon the condition of the tools being used for the process. So, there is a general agreement on arbitrary rule that the process mean may shift 1 plus 1.5 sigma to the right or 1.5 sigma to the left. This arbitrary figure has been taken by the people who have given us the 6 sigma philosophy. If we shift this mean, process mean to right side, and we will get a picture as shown in the slide. And we are now discussing the statistical background regarding the 6 sigma process. Our customer specified limits remain as such, LSL and USL spread over plus minus 6 sigma, but our process is only spreading around plus minus 3 sigma. Now, we have shown that a shift in the mean has been shifted by 1 plus 5 sigma, and this has been shown by a dotted line, and the mu is written on this dotted line. If such is the case, on the right hand side 6 sigma will not be 6 sigma, we will subtract 1.5 sigma from this level, and we will get only 4.5 sigma. If from the normal tables we look at the figure at 4.5 sigma, we will get a different picture. If we assume a 1.5 sigma shift to the right, the yield is the area under the normal curve. To the right of 1.5 sigma are about 0.9332. Suppose now that the process variation is reduced and it is 0.002, there is now plus minus 6 sigma between tolerance limits, and the process can be called a 6 sigma process. What we have discussed now, our customer specification was 0.004 as sigma level, but we have changed the process in such a way that it is running so precisely that the sigma is only 0.002, which is just half of the specification given by the customer. If such is the case, we call the process running at Six Sigma level. To calculate the yield for Six Sigma process, we allow the mean to shift plus minus 1.5 sigma as we have discussed earlier. Suppose the mean shifts by plus minus 1.5 sigma to the right. So, the yield is the area under a normal curve to the right of 4.5 sigma, and this 4.5 has come by subtracting 1.5 from 6 sigma level, as we are now maintaining a shift in the mean value. This area is now 0.99966. Now, we can easily calculate the defects, which will be obtained by subtracting this figure from 1, which is only 0.00034, or in other words 3.4 ppm, parts per million. Now, it clearly explains the value 3.4, which is associated with Six Sigma level. Where from this 3.4 has come, we have clearly explained by shifting mean 1.5 on the right hand side, and the limits now become not 6 sigma, only 4.5, and the area beyond 4.5 from the normal tables gives us defective items produced will be only 3.4, and this is the figure which has come with this explanation. This is often quoted figure for a Six Sigma process. This is rather theoretical figure. We will call it only theoretical figure, because actually the shift in the mean is not exactly 1.5 sigma. Sometimes maybe it is less than 1 sigma, but we have taken this figure as a arbitrary figure. And no process is truly normal to the 6th decimal place. We cannot have any process which is running or the data are distributed normally to the 6th decimal place, which we have already calculated. But for calculation purposes, we have taken this arbitrary figure, and with this arbitrary figure of 1.5 sigma shift, we shall be producing only 3.4 ppm defects. If such is the case in the process, this will make the process running at 6 sigma level. Now, we will discuss another model, Kano model, which has been given by the Kano. Origin of the Kano model, Kano was a professor at Tokyo Rika University in Japan. He is internal consultant, and he has already received Deming Prize in 1997. And he has given the idea of voice of customer. What is voice of customer? That is regarding the needs and the requirements and the wants of the customer. Customer gives something that it should be there in the product or it should be there in the process, and that particular thing is known as voice of the customer. Kano developed foundation for an approach on attractive quality creation. This particular word has come from Kano only, which is attractive quality creation, commonly referred to as Kano model. Challenged traditional customer satisfaction model, and traditional one is customer satisfaction model, and Kano has given us attractive quality creation. That more is better. As per Kano, more is better. We should give more and more to the customer, and which is considered always better than the traditional way of satisfying the customer. The more you perform on each service attribute, the more satisfied the customers will be, and this is given by Kano. Proposed new customer satisfaction model. Performance and product and service attributes is not equal in the eyes of the customers. One attribute is liked by the customer, but the same attribute may not be liked by other customer. Performance on certain categories. Attributes produces higher levels of satisfaction than others. One attribute may give more satisfaction to one customer and less satisfaction to the another customer. And while selecting the project, we take care of Lean Six Sigma while using Kano model and design for Six Sigma. We design the product taking into account the Six Sigma philosophy, and new product development, new service development, determine market strategies. We use Kano model. Now, we will discuss the key models, key elements of Kano model. First, identify the voice of the customer, what exactly is needed by the customer. Translate voice of customer into critical to quality characteristics. This we discussed in yesterday's class. CTQs, the things or the attributes which are critical to quality as per customer's requirement. Rank the CTQs into 3 categories. Then we have to categorize, prioritize these CTQs. We will call them dissatisfier, satisfier and delighter. Dissatisfier is a must be CTQ and cost of entry. Satisfier, more is better. Satisfier attribute will be concerning regarding more is better and competitive. Delighter, latent need, differentiator from one product to the other product, and then evaluate current performance. I will repeat the yesterday's example because it is as per the Kano model. Suppose you go to a coffee vendor and ask for a cup of coffee. That is your stated need, and this is a dissatisfier, because if he does not give you the coffee, you will not be satisfied. Satisfier is if he provides coffee and a napkin, and it will make the supplier competitive in the market, because he is providing napkin also. Then delighter will be if a cookie is also given along with cup of coffee and a napkin, then this will delight the customer. As per Kano, we are to delight the customer. We are not to stop at dissatisfier, we are not to stop at satisfier, we are go beyond these, and we are to achieve delighter, and we are to delight the customer. Evaluate current performance, and this graph shows the Kano model. On x axis, service performance is written, whether it is good or bad. Bad is on the left hand side, good is on the right hand side, and then customer satisfaction is on the y axis. Up positive values means satisfaction and negative values dissatisfaction. If we concentrate on the first quadrant, where service level is positive and the satisfaction level is positive, we call them satisfier, one dimensional desired quality. And if we consider the same graph, positive value on the satisfaction side and the negative value on the service performance side, we go to the second quadrant. Delighters, excited quality. Didn't know I wanted it, but I like it. Similarly, third quadrant, bottommost on the right hand side quadrant, where service level is positive, where satisfaction level is negative. Dissatisfier, and this is a must be expected quality. We have to have this feature in the product, because if it is not there, it is going to dissatisfy the customer. So, this we can say that cannot increase my satisfaction, but can decrease. This will not increase the satisfaction, but if in the absence of this particular attribute, this is going to dissatisfy the customer. The Kano model is a theory of product development and customer satisfaction developed in the 80s by Professor Kano, which classifies customer preferences into 5 categories. These 5 categories are given by Professor Kano, and these categories are attractive, one dimensional, must be, indifferent and reverse, and we can add quality word along with these 5 items, like attractive quality, one dimensional quality, must be quality, indifferent quality and reverse quality. These categories have been translated into English using various different names like delighters, oblique exciters, satisfiers, dissatisfiers, etc., but all refer to the original articles written by Professor Kano. What is attractive quality? Attractive quality, these attributes provide satisfaction when achieved fully, but do not cause dissatisfaction when these are not achieved. These are attributes that are not normally expected in the product or service. For example, a thermometer on a package of milk showing the temperature of the milk is not required by the customer. Since these types of attributes of quality unexpectedly delight customers, they are often unspoken, they are not written also. If it is provided, customer is going to be satisfied. If it is not provided, it does not mean that the customer will get dissatisfied. And now we will talk about one-dimensional quality, and these are given by Professor Kano only. One-dimensional quality, these attributes result in satisfaction when fulfilled and dissatisfaction when not fulfilled. These are attributes and these are spoken ones. An example of this would be a milk package that is said to have 10% more milk for the same price. It is written on the package that you are getting 10% more milk in the same price which the supplier was charging before also. But instead of saying 10%, if you find that it is less than 10%, this is going to dissatisfy the customer. He is not getting more satisfaction by extra 10%, but he is going to get dissatisfaction by getting less than 10%, which is claimed by the supplier. And this particular one is called one-dimensional quality. Now, we will discuss something which is called must-be quality. Must-be quality, these attributes are taken for granted when fulfilled, but result in dissatisfaction when not fulfilled. And these particular attributes, one feels that these are there in the product if the product is sold. An example of this would be package of milk that leaks. We do not want any leaking package. Customers are dissatisfied when the package leaks, but when it does not leak, the result is not increased customer satisfaction. Since the customer expect these attributes and view them as basic requirements, then it is unlikely that they are going to tell the company about them when asked about quality attributes. They feel that this is a must be quality and it should always be there in the product. They are not going to ask the company, they are not going to mention it to anyone. If it is leaking, it is going to dissatisfy it. Means leaking means absence of these kind of attributes will make the customer dissatisfied, and the presence is a must as far as customers are concerned with this particular must be quality attribute. And then indifferent to quality. Indifferent quality, these attributes refer to aspects that are neither good nor bad, and they do not result in either customer satisfaction or customer dissatisfaction, and these kind of attributes are called indifferent quality. Now, there is one more term which is reverse quality. Reverse quality, these attributes refer to a high degree of achievement resulting in dissatisfaction and to the fact that not all customers are alike. For example, some customers like high-tech products and some customers really do not like high-tech products, because they feel that basic requirement is being fulfilled by a basic model. Why do they go for high-tech products which are very costly and difficult to operate also? And this is the thinking of some of the customers, and these kind of attributes are called reverse quality. For example, some customers prefer high-tech products while others prefer the basic model of a product and will be dissatisfied if a product has too many extra features in it, because they feel that these are difficult to operate and we should not have the product with high technical features. And there is another way of explaining the Kano model process, and it takes care of 4 particular things: research, analyze and brainstorm, plot and diagram, and strategize. Under research, research available data sources, determine data collection strategy, design data collection instruments, collect and summarize data. And under analysis and brainstorming, analyze results from the data collection, brainstorm list of features and functionality, develop functional and dysfunctional questionnaire, distribute questionnaire, and plot and diagram. Under plot and diagram, develop customer requirement matrix, record questionnaire results in matrix, plot results on Kano model, as we have given satisfaction, dissatisfaction, service performance. And strategize, determine project selection. Based on this, we will select the project, product development, service development, identify marketing strategy. This is the complete Kano model process. Research. Under research, must-be's, focus groups, lawsuits and regulations buzz on internet. Must-be's are given by these regulations which the government has provided. And satisfiers, we will identify the satisfiers, competitive analysis, interviews, surveys, search logs, usability testing, customer forums. And the delighters will come from field research, marketing, branding, vision, industrial design, packaging, call center data, site logs. And then we will have plot and diagram. Based on the identified say satisfiers, dissatisfiers, etc., we will have the diagram which has been given by Kano. We will prepare this diagram and find out where exactly we are to operate. Strategize. Project selection, we will select the project, Lean Six Sigma, design for Six Sigma, and then organizational strategy. Dissatisfier, must be cost of entry. Satisfier, more is better. We will identify these attributes which are dissatisfiers, satisfiers and delighters. Delighters are of course latent needs which are not given by the customer, and differentiators. These are the differentiators from one competitor to the other competitor. Application, break into teams, select team leader. How to go about Kano model? First, break into teams, select team leader, select scribe. Scribe is who is going to record the minutes of the meeting. Select presenter. Scenario, you work for a hotel chain and your company is trying to identify voice of the customer, information to improve hotel performance. Customer will give his requirements, his needs and his wants, and those will be recorded as voice of customer. And then instructions, brainstorm important characteristics you expect when staying at a hotel. Identify whether they are a must be, expected or a delighter from a business client perspective and from a vacationer perspective. Add in what the current performance is for the hotel and then work for Kano process. Now, we will summarize what we have discussed so far. Analyze and rank the voice of the customer and prioritize CTQs, critical to quality attributes given by the customer. Develop into categorize them and find out what attributes are required as dissatisfier, what are required as satisfier and what are required as delighters. Identify and implement strategy. Now, we will discuss some tools and techniques which are part of the quality control system. Some people call these QC tools, quality control tools, and simply 7Q tools also, and some people call these tools as 7B tools, 7 basic tools. And these all tools are part of Six Sigma. Let us discuss one by one. And all these tools will not be discussed here because we are covering the course as per the green belt, and soon we will discuss who are called green belts and basic things which are available we will be discussing in this series of lectures. First one is 7 QC tools, 7 M tools. M stands for management, 7 management tools. Process capability analysis, acceptance sampling, SQC and SPC. SQC is statistical quality control and SPC is statistical process control. Then test of significance and analysis of variance. Analysis of variance is commonly known as ANOVA. Design of experiments and Taguchi methods. Regression analysis, quality function deployment, failure mode effect analysis, benchmarking, BPR and GIT, Kano model, tree diagram, CPOC and process mapping, and then DUMAC. These are some of the tools available under Six Sigma, and we shall be discussing now only Q7 tools, which are also called QC7 tools. And these 7 tools, if used properly, they will make the process closer and closer to Six Sigma level. The first one is cause and effect diagram. Next one is check sheets, control charts, histograms, Pareto diagram, and 7th one is the scatter diagram. We make use of all these tools to solve the problems, modify the processes and achieve Six Sigma level. And these tools are called quality control tools. Similar to quality control tools, M7 tools are also available. These are called management 7 tools or 7 management tools. And these are affinity diagram, relationship diagram, systematic diagram, matrix diagram, matrix data analysis, PDPC, process decision, program chart and arrow diagram. And these are called management tools. Now, we will discuss our QC7 tools. The first one is cause and effect diagram, which is also known as fishbone diagram. The diagrams looks like the bones of a fish. Spine is there and the face of the fish is there. On the face of the fish, we write the problem for which we are finding the solution. On the spine, we show the major bones. Major bones are the reasons for the problem. It can be men, machines, material. So, these we write on the major bones connected to the spine. Then we write minor bones. So, maybe under material, we have different problems. Material is not as per specifications. Material delivery is not on time. We write these on the smaller bones, and this completes the fishbone diagram for a particular problem. Looking at this diagram, we have identified what exactly is the problem which is causing the main problem. Then we identify those only points which needs rectification. For this, we brainstorm, we make the affinity diagram, we find the solution to the problem, we implement the solution, and finally, the problem is over. This is also known as fishbone diagram, cause and effect diagram, also known as Ishikawa diagram. Ishikawa is a person who has given the idea of this cause and effect diagram. Just look at this. Now, how to construct this fishbone diagram? First step, step number 1, identify the problem for which we are finding the solution. Then step number 2, draw spine and bones. As we have already discussed, show the spines and bones, and on the face of the fish we write the problem. The problem is shrinkage, and it is written as high inventory shrinkage at local drug store. There is a drug store and that fellow is facing shrinkage of inventory. And who can contribute this problem? Like employees can give the problem, shoplifters can give the problem. So, these will be written on the main bones. Next is, as far as the employees are concerned or the shoplifters are concerned, what sort of problems they can have. So, those are written on the small bones, like anti-theft tags poorly designed. This is a problem. Expensive merchandise out in the open and no security surveillance is there. These are the minor problems, and these are written on the minor bones of the fish. Now, if we complete the diagram, this looks like this particular diagram. The problem is employees, shoplifters. Employees can have attitude problem, training and practices. Training is not adequate, or new trainees have been added to the shop floor, expensive merchandise out in the open, no security surveillance, and this completes the diagram. Whatever problems are applicable to this particular case, those will be highlighted and a solution will be found for these. So, step 5, use the finished diagram to brainstorm solutions to the main problem. This completes the cause and effect diagram or fishbone diagram, or it is also known as Ishikawa diagram. Now, we will discuss check sheets, which is another tool out of 7 QC tools. Check sheets, on a piece of paper, we write certain things regarding the problem. Suppose a company is facing a very simple problem of leaking taps, and this problem is to be rectified. How to rectify it? And somebody has suggested make check sheets. First, number all the taps available in the factory, 1, 2, 3 like this. If 100 taps are there, make a list of 100 taps. Early in the morning, somebody should go and find out which tap is leaking and which tap is not leaking. On that piece of paper where we have the numbers 100 available, we will write tick or cross, tick for not leaking taps, cross for leaking taps, and this will complete the check sheet. Every day this kind of check sheet will be seen, and it will be seen that how many taps are being rectified on daily basis, how many taps are leaking on repeatedly basis, and this will be given by check sheet, and somebody will be assigned job of rectifying the leaking defect in the taps. There are 2 types of check sheets, ordinary check sheet and locational check sheet. In locational check sheets, the diagram of the product which is being inspected is also drawn on the piece of paper. Now, in the case of say leaking taps, on a plot plan, these taps and their locations are shown, and on each location again a tick or cross is shown. You can have red mark or a green mark. Red shows that the problem is there, green mark shows that there is no problem. If we have more red marks in certain location, that particular location is giving defects. So, somebody will have to concentrate in that particular area to remove the defects. Similarly, if we are inspecting shoes which are being manufactured by a shoe manufacturer, we will have a diagram of shoe made on the check sheet, and if we want to note the defects, every time we take a sample of say 5 pair of shoes and mark their defects on the diagram. Maybe the toe is giving the problem, lower sole is giving the problem, laces are giving the problem, upper is giving the problem, we will put a mark for any problem found in this particular area. Now, looking at this check sheet, we shall be able to know that which particular area is giving more problem. If the toe is giving more problem, we will have more marks written on the toe. If the upper is giving problem, we will have more marks written on the upper. If lower sole is giving problem, we will have marks on the lower sole. This is called locational check sheet. And going back to the leaking tap problems, this is the check sheet for leaking tap problems. And I have shown 13 such taps, and they are numbered 1, 2, 3 and up to 14. And on the other column, tick and cross is written. Tick means there is no leakage, cross means it is leakage. And this is check sheet. Now, we will discuss something regarding control charts, which is another tool which is part of QC7 tools. In control charts, we inspect the process on regular basis. Before we go into the depth of control charts, we have to discuss quality control, which includes the activities from supplier through production and to the customers. Incoming materials are examined and finished products are also examined. The quality of partially completed products are analyzed to determine if production processes are functioning properly or not. Partially completed products are also known as semi-finished products. Raw material, semi-finished products and the finished products. Finished goods and services are studied to determine if they meet customer requirements, customer expectations or not. And this is part of quality control, and this is achieved by using control charts. When to inspect during the production process? Inspect before costly operations. If the operation is very costly, inspect the material before it enters the costly operation. Inspect before operations that are likely to produce faulty items. Inspect before operations that cover up defects, and inspect before assembly operations that cannot be undone. Once it has been done, it cannot be rectified. So, we must check the products before assembly operations. On automatic machines also, inspect first and last pieces of production runs, but few in between pieces also be inspected, and then finally inspect the finished products. Now, there is a central limit theorem which says that sampling distributions can be assumed to be normally distributed even though the population means lot distributions are not normal. One is called population. Population is the entire lot of products or lot of material which has been received, and the sample is a sub portion of the population. A sample has been taken from the population. Another example of population and sample is, there is a class of 50 students and 50 students will make a population. If we take a sample of 5 students, this sample is called taken out of the population, and this is a sample which finally shows the qualities of the main population if it is taken at random. The theorem allows use of the normal distribution to easily set limits for control charts and acceptance plans for both attributes and variables. I have introduced these two words, attributes and variables. Attributes have the figure defect. We say the statements defective, non-defective, yes or no, and these are quality related statements. But variables, the items which can be measured by using a scale, these are called variables. We have two types of variables, attributes and variables, and then two types of control charts also for controlling the quality of these attributes and variables. Again, control charts. Primary purpose of control charts is to indicate at a glance when production processes might have changed sufficiently to affect product quality. Process is running, we should be able to know that process is running with proper specifications, and if it is not running at proper specification, we should be able to know it, and the control charts are there to tell us whether the process is running without any problem or with some problem. If the indication is that the product quality has deteriorated or is likely to, then corrective action must be taken before it gets deteriorated or before it starts producing defective parts on a large scale. If the indication is that product quality is better than expected, then it is important to find out why so it can be maintained. Use of control charts is often referred to as statistical process control or statistical quality control. Then constructing control charts. Vertical axis provides a scale for the sample information that is plotted on the chart. Horizontal axis is the time scale. At time interval, we take the reading of the process. Horizontal center line is ideally determined from observing the capability of the process, and that gives the mean value of the process. Two additional horizontal lines are drawn. The lower and upper control limits typically are 3 standard deviations below and above respectively of the center line. So, we run the process with plus minus 3 sigma limits only. If the sample information falls within the lower and upper limit, the quality of the population is considered to be in control, otherwise quality is judged to be out of control and corrective action is required. It is obvious that we have drawn two limits, lower control limit and the upper control limit, which is the area where we operate the process. If something is beyond these limits, then we say that these are defective pieces. Process is not properly running and the defects are being produced by the process, and the corrective action is to be taken immediately. Two versions of the control charts will be examined. First one is control charts for attributes, which we have already told what is the meaning of attributes, and the control charts for variables. We have already discussed attributes and variables. Control chart for attributes. Inspection of the units in the sample is performed on an attribute, as already discussed, defective, non-defective. That is the only information we get from the inspection. Information provided from inspecting a sample of size n is % defective. In a sample of P are the number of units found to be defective in that particular sample and divided by n. Control charts for attributes. Although the distribution of sample information follows a binomial distribution, that distribution can be approximated by a normal distribution. So, we shall be using normal distribution, though it follows binomial distribution, and with the mean of p and standard deviation of sigma. The 3 sigma control limits are then p bar, which is the mean, plus minus 3 under root p into 100 minus p divided by n. This will give us two limits for the control charts, and the control chart will be drawn with these two limits and a mean value. Mean value is given by p bar. Let us have some example to illustrate this particular control chart. Say every check cashed or deposited at XYZ bank must be encoded with the amount of the check before it can begin clearing process. The accuracy of the check encoding process is of utmost importance. If there is any discrepancy between the amount a check is made out for and the encoded amount, the check is called defective. So, now we have a way to check the process, defective, non-defective checks. We will check the process and find out defective and non-defective checks. Say out of 20 samples, each consisting of 250 checks, each sample size is 250 and we have checked 20 such samples and examined them properly. The number of defective checks found in each sample is shown below. Here we have the readings available. There are 20 samples and the defective checks which are found are written here, 41532745523, the first 10 and then next 10 also written. So, So, 20 samples and their defectives are recorded like this. And now, we will have the control chart. The manager of the check encoding department knows from past experience that when the encoding process in control, an average of 1.6% of the encoded checks are defective. He wants to construct a P chart with 3 standard deviation control limits. How to make it? We have already discussed the formula. Upper control limit P plus 3 sigma P bar and lower control limit is P minus 3 sigma P bar. P is nothing but P bar, mean. In our case, as the process is running with 1.6% defective sigma. So, 0.16 plus 3 into 0.007936 is equal to 0.039808 or finally 3.98%. Similarly, the lower control limit comes out to be 0%. So, our lower control limit is 0%, upper control limit is 3.98%. So, with these limits we shall be operating the process, we shall be taking out a sample of 250 checks and finding out how many defective are there, and the percentage if it goes beyond 3.98% will stop the inspection process immediately to see where exactly the things have gone wrong, and those will be modified because our limits are 3.98% and 0%, and 3.98% has come from our past experience. And the control chart will look like this. Particular slide shows the attribute control chart for defective checks. Control chart for variables. Now, we will discuss the control charts for variables. Under this, inspection of the units in the sample is performed on a variable basis. The information provided for inspecting a sample of size n is, first we have sample mean x bar or the sum of the measurements of each unit in sample divided by n. Range also we will get range r of measurements within the sample or the highest measurement in the sample minus the lowest measurement in the sample. Say for example, our sample size is n, we take a sample of n items from the running process and we check the dimension x. We add all the dimensions and divide by the number n, we get the mean value of n. Similarly, for range, highest value of the measurement and the lowest value of the measurement, and the difference is the range. And we check samples after samples, we take a mean of the samples, that gives us the r bar, average value of r, and parent value of the mean also x double bar. Each sample we take a mean, and say if we have taken 5 samples and final means are added and the number of samples taken and the number is divided and we get the grand mean, and this x double bar is also known as grand mean. Grand mean is a horizontal line and then we draw upper control limit and the lower control limit. In this case, 2 separate control charts are used to monitor 2 different aspects of the process's output. Central tendency, variability. We have to check the central tendency is given by the x bar chart, variability is given by the r bar chart. Central tendency of the output is monitored using the x chart, variability of the output is monitored using the r chart. The central line x double bar, the sum of the number of sample means collected while the process was considered to be in control divided by the number of samples, which we have already discussed. The 3 sigma lower control limit is x bar minus a r. A is a constant which depends upon the sample size and the tables are available. R is the average value of the range. Similarly, the 3 sigma upper control limit is x double bar plus a r. Same thing, a is a constant which is noted from the tables and which depends upon the sample size. Factor a is based on the sample size, which we have already discussed. R chart, similarly R chart, the 3 sigma lower control limit is d1 r, d1 is again a constant, the 3 sigma upper control limit is d2 r. Factors d1 and d2 are based on sample size, and this shows the table from which we get the values of a, D1 and D2. First column shows the sample size, next column for sample size, sample mean A values are given, and for sample range D1 and D2 values are given. And from this table, depending upon the sample size, we get the values of A, D1 and D2. Variable control chart. An example, say Mr. Kapoor wants to construct X bar and R bar charts at the bag filling operation for cement company. He has determined that when the filling operation is functioning correctly, bags of cement average 50.01 kg and regularly taken 5 bag samples have an average range of 0.322 kg. Range is also given and the mean is also given, and we have to construct the control chart. X double bar 50.01, range is also given 0.322 and the sample size n is 5. Now, upper control limit X bar plus AR. This is a formula we have already discussed, and this will give us 50.01, which is the mean value already established, plus 0.577, it is the value of A taken from the table and multiplied by 0.322, which is the average range. The value becomes 50.196. Similarly, lower control limit X double bar minus AR, and we will calculate this the same way that we have calculated upper control limit, with the difference that minus sign will be used, and this value is 49.82. Now, we have two values, one is upper control limit and the lower control limit with an average value which is shown on the horizontal chart. And this chart is the variable control chart for sample means, and the next one is for range also. So, now we have variable charts for sample range and the sample mean. These two charts we have discussed just to demonstrate the use of control chart. First one was for attributes, and these two charts are for variables. Now, this only demonstrates the use of control charts. People now use other control charts also. Okay? One when gets experience, then the fellow can also learn how to use other charts and what other charts are also available. Maybe this is covered in the course of black belts and the master black belts. Now, today's lecture we are finishing right now here only, and the next lecture will discuss things which are much serious and which are used in the Six Sigma process, and how to implement Six Sigma, and further details will be discussed in the subsequent lectures.